The setup of this problem is actually pretty simple, but the solution, the mathematical solution of solving for three different variables is going to be a little bit more difficult. So what I'm going to do is I'm going to break up this video into two parts. The first would be just setting it up, and then the second part will be trying to solve a system of equations using the matrix method. And that's basically with inverse matrices and whatnot. Now, you can solve it using substitution as well, but I'm not going to talk about that since that's kind of a math concept. But I will use matrix method since it might be new and possibly useful. So what we have is a crude drawing of the circuit that you saw in the last slide. There are three components where we can analyze the current. The current going through the top part and thusly the bottom part leading up to the battery, the current going through the middle as it's split up, and the current going to the right and around the loop back over this way. That's all going to be the same current. Now, I went ahead and defined where I think the current's going to go. Now, this doesn't matter. So if you solve for current and you assume that the current flowed this way and down and then to the right as well, and then met up down here to go back to the battery, if you assume that the flow of current was that way and you happen to get a negative number for say I3, then that means you know that the current is going the other way. So what you first do is take a wild guess which way you think current's going to go. If you're wrong, your I will be negative, no big deal. Secondly, I'm going to go ahead and break up the setup into three parts. I will use Kirchhoff's loop law for the left loop, the loop law for the right loop, and then the junction law for this little junction right here. I put 2 points down because these are points in which I'm going to start my two loop laws. I'm going to start the first left loop law from the top left corner. I'm going to go around this loop and there. Then for my right loop, I'm going to start with the top left corner of this loop, go around, and go back up here. Now, the Kirchhoff's loop law is about voltage addition. The Kirchhoff's junction law is about current addition. So they're two different things. Let's go ahead and do the loop law first. First for the upper left corner of the left loop. And first, when assumed current, so this is an assumption, when the assumed current flow goes this way through a resistor, a voltage is going to drop. So it's going to be a negative IR. That's why I'm going to put a negative symbol here with a positive I value, or assumably positive I value, and a positive 4. This is IR, and it's a negative because of the voltage drop. I'm going to go ahead and omit the units of ohms just for simplicity and just to get the equation going. Next, I noticed that you're going to go through, in this loop at least, you're going to go through I2 and this resistor of 2 ohms. So you're going to drop voltage again. You're going to do minus I2 times the resistor value of 2 ohms. Next, you're going to go down here. Nothing's going on, no obstruction. And then to get back to the same point, you're going to have to jump up. So from small line to big line is a positive voltage jump of 28 volts. And as you go around the circuit, you're going to have a net zero change in voltage. So from here to here is 0 change in voltage. So all of this voltage subtraction and addition from the battery all ends up to be a net 0. So that's the first loop. Now the second loop is going to start from here, and it's going to be a little trickier because of the fact that we're going against the flow of current. So you might be able to figure out what you need to do for this, but I'll explicitly tell you as I'm going along with this. So from this point and going clockwise, you're going to have a a voltage drop, which is a negative IR. So you're going to then have an I3, which is the current going through this branch, times 1. And it's a negative since the voltage is dropping as the current flows to the right. Next, you're going to go through the battery, but the battery is from long stem to short stem. So the battery is trying to make current flow this way. This is a voltage drop through a battery. That's different from this voltage gain as we did on the left loop. So because we're going from long stem to short stem, it's a voltage drop. So it's going to be a negative 7 volts. And now for this part right here, you could see that you're going to have to go up through this resistor to go back to the same point and have the equation equal to net 0 volt. But we are going against current. So instead of a voltage drop, we are going to have a voltage gain. So instead of a minus I2 times 2, we're going to have a plus I2 times 2. And that's our second equation. So for the third equation, you see that we kind of ran out of loops. Yes, we can go ahead and take this big loop, but I'm going to argue that you're going to have the same terms. You're going to have I1 times 4. You're going to have I3 times 1. You're going to have 7 and 28. So it's actually not a new equation. It's kind of a different way of writing the first two equations. So you're not going to get any new information out of that, and it won't serve as a useful equation in your set of equations. So you have three variables, I1, I2, and I3. You have two equations so far with two unique loops. Now you got to use the junction method in order to find the third equation. The junction method deals with current only. So the current in I1, so the I1 current looks like it's breaking off into I3 and I2. Ergo, I1 is equal to I2 plus I3. So in other words, you could say I1 minus I2 minus I3 are all equal to 0. Because if you put these two on the other side, it's the same as saying I1 is equal to I2 plus I3. So there we have it. We have three unique equations and three variables. So now it's the math part. Normally, and generally, this is not frowned upon at all. You can do this. You can go ahead and solve for the system of equations by substitution. And that's how most of you are familiar with it. So that is solve for I1 with respect to I2 and I3, plug it into here. You can solve for I3 with respect to I2, plug it into here, and then solve for I2 with respect to just a number. Get I2 as a value, plug it into the variable here, solve for I1 in terms of a number, plug it into here with I2 that you already know, and then solve for I3. So you can use substitution just, as well as you want. It will take a while, but it's definitely true, tried and tested, and it's definitely legitimate math. What I'm going to do, however, is invoke matrices. So let's go ahead and get this into more familiar terms, or at least the terms that are more conducive to using matrix operations. So what I'm going to do is I'm going to put it as a function of, or a I1 parameter, I2 parameter, I3 parameter equals a number. And this would make the equation a little bit nicer. So we're going to have 4I1 minus 2I2 plus 0I3, since there's no I3 component, you could just put a 0 in front of it, equals, put 28 on the other side, negative 28. Just to make it nicer, I'm going to go ahead and multiply both sides by negative 1 so I can get rid of all of these negative signs. For the second equation, I'm going to go ahead and do the same thing. Negative 1I3 plus, oh, I'm sorry. There's going to be no I1, so I'm going to go ahead and say 0 I1 plus 2 I2 minus 1 I3 is equal to take this -7, put it on the other side, plus 7. I'm not going to switch things around or multiply anything by -1 since I'm pretty happy with the simplicity of this equation. And then the third one, it's pretty simple. I'm just going to copy this over. I1 minus I2 minus I3 is equal to 0. So now I have an equation that aligns the I1s, I2s, and I3s and the non-associated numbers of the equation. And what you can do is you could form a matrix out of that. So what we have here is a matrix of a 3 by 3 whose elements are on the top row is 4, 2, 0. Those are the coefficients on the first equation. 0, 2, -1, coefficients of the second equation. And then 1, -1, -1, coefficients of the third equation. And then you have the parameters that you're trying to solve for. I1, I2, I3. Now, based on matrix multiplication, you have 4 times I1 plus 2 times I2 plus 0 times I3. You have 0 times I1, 2 times I2, -1 times I3, and so forth. And it all breaks down into the same thing that we have here when you do the correct matrix multiplication right here. And I'm going to set this equal to a set of 3 here, 3 rows, 1 column. It's going to be 28, 7, and 0. Okay. So it's basically like saying 4 times I1, 2 times I2, 0 times I3 is equal to the first element. Then the same operation is equal to the second element, and the same operation on the third row is equal to the third element. So it breaks down back into here. Now what I can say is that this, we'll just call this a name. So we'll say that this matrix is M. This vector is R, and then this vector is K. I think it's a column vector or a row vector. I think it's a column vector. So basically what we're trying to solve for is the vector R. You do that by taking an inverse matrix of M, putting it on the other side. So mathematically speaking with matrices, R is equal to inverse M times K. And that's easy enough to solve basically. Last point, though, is what is inverse M? Inverse M is defined as 1 divided by the determinant n times CT. CT is the matrix of cofactors of the matrix M. So we'll get to that in just a second. And then we're taking the transpose of the matrix of cofactors of M. So let's get into that one at a time. First, we got to figure out what the determinant of M is, and then we'll deal with this later. The determinant of M is basically this operation here. It is the first element in the first row multiplied by the cofactors of M. I wonder if I got that word right. So basically, to find the determinant of M, let's go ahead and just solve that here. For example, it's going to be then 4 times the cofactor of that particular element. So that means that we're taking this element, we're crossing this part off, we're crossing this part, and we're only looking at the cofactors here. That's going to be 2 times -1, so that's -2, minus -1 times -1, which is +1. Okay, so the determinant is this times the cofactors with these 4 elements here. Now, for the second element, there's a minus. So it's going to be -2 times the cofactor of that element, which means you're going to take the same operation, but with all elements that are not within the same row or column of this subject element. So that's the 0, -1, 1, -1. So the part that goes in the parentheses is 0 times -1 minus -1 times 1, which happens to be then +1. Now for the third column in the first row, we're going to add again 0 times the cofactor of that element, which happens to be with these four numbers. At 0 times -1 minus 2 times 1. It really didn't matter since this was 0. I just wanted to show how that works. So the determinant of m is going to be one number, and that's going to be -14. Okay, now here's the tricky part. The matrix of cofactors. So every cell here, every cell in the matrix of cofactors, which I'm going to go ahead and just draw out the framework here, is going to be the cofactor of that particular element of M. So for example, in the first element of this 3x3 cofactor matrix is going to be the cofactor of 4, which happens to be these four numbers. As we've discovered, it's going to be 2 times -1 minus -1 times -1. And that's just going to be -3. Second element in the first row, or the second column in the first row, is the cofactor of 2, which we already found it to be -1 here. And it's -1 because the negative carries over every other element as you go down the row. So this is going to be a positive value of whatever the cofactor is. Is going to be the negative value, whatever the cofactor is. And then this is going to be a positive value again. So the third element is going to be the cofactor of this, which is going to be 0 times -1 minus 2 times 1. That ends up being -2. Now for the second row, it's the opposite. So if this is a positive, this is negative, this is positive. This is a negative, positive, negative. Okay? And the third row will go back to the first, positive, negative, positive. So the second row, first column is already going to be a negative of whatever the cofactor is. So the second row, first column is going to analyze these four numbers. 2 times -1 is -1, or sorry, -2, minus 0. So the answer is -2, except it's a negative of that. So it's actually a positive. The second is the middle. So that means that we will work with 4, -1, 0, and 1. 4 times -1 is -4 minus 0. And in this case, it's a positive, so there's no negative added to it. It stays -4. This one, we have -4 minus 2, and that's going to be -6. But there's a negative attached to this particular column. Remember, positive, negative, positive, negative, positive, negative. So instead of a -6, it's a -6, and that's a +6. For this one, it's a positive of cofactor with these four numbers, -2 minus 0. For here, that's -4, but it's a negative of -4. And then for here, it's 8 minus 0, and it's the positive value, so it's 8. And lastly, the transpose of this matrix of cofactors is where the row becomes column and the column becomes row. So the first row becomes the first column, and the first column becomes the first row. So it's just going to be -3, -1, -2, then +2, then -4, and and then 6, and then -2, 4, 8. So you can see that as I went across this first row, I now made this become the first column. second row became the second column, third row became the third column. So this is now the transpose of the matrix of cofactors. Let's get a new piece of paper. Okay, so now that I got a new piece of paper, it's actually the backside of the first. I'm going to go ahead and finally solve for the inverse M1 matrix, and that is 1 divided by the determinant of M multiplied by the transpose of the cofactor matrix. So that's going to be 1 divided by negative 14 multiplied by each of these 9 elements, and I'm going to put it all in the as elements of this inverse matrix of M. I already went ahead and calculated it, so I'm just going to write it down for you and move on from there. Here are the values I got by taking each of these elements and divided by negative 14. It's going to be kind of a weird number, so it's not going to look comfortable. And then lastly, what we're going to do is we're going to say that the R column vector is going to be this here matrix multiplied by K. If you remember what K is equal to 28, 7, and 0. So now what we're going to do is we're going to multiply inverse M by K. And how you do that is by simple matrix multiplication. So R is going to equal to this number times this number plus this number times this number plus this number times this number. That's going to be the first row. It so happens that if you were to take the addition of these products, you get 5. Nice and pretty. Now for the second row, you take the second row of the inverse M matrix. You take this number times this number times this number, and this number times this number. And it ends up being 4. And then lastly, for the third row, you take this number times this number times this number, and this number times this number, and magically you get 1. There you go. So this tells you right here, here's your answer, that I1 is 5 amps, I2 is 4 amps, and I3 is 1 amp. And the cool thing about that is that these are all positive. So what does that mean? That means that the original way that I drew the current going around this loop is correct. So the current goes this way, splits off into these 2 branches, rejoins in the back. This is 5 amps, this is 4 amps, and this is 1 amp. Here's a short summary of the work.